So now that we know how to do confidence intervals with means, I want to talk about how to do a hypothesis test for means. And as you can imagine, this is going to be very similar to what we did last week when we dealt with proportions. We're going to check our conditions, and then we're going to state the model, which is of course our student's T model, and we're going to list our test, which is a one sample T test. Sometimes that will include an interval. We're going to write our hypotheses, which we're going to use mu instead of p, because obviously last week we were finding p, which is the population proportion. This week we're trying to capture mu, which is our population mean. Just like last week, we're going to write the value and in words. Our calculations will be to find the standard error, to find the t-score. This, remember, is called our test statistic. So if they ever ask you for that, that's just fancy terminology for you find your t-score. Remember, with this t, typically we're going to write a subscript that includes the degrees of freedom. And then we're going to find our p-value either using our calculator, which will be t-CDF, lower, upper, just like we did with normal, but then we also include our degrees of freedom. Or we're going to use StatCrunch, and that's just using the t calculator. So I'll show you how to do both of those. Then we'll write our conclusion just like last week. So again, if the p-value is smaller than alpha, and again, unless they specify, we're probably using 0.05, but we'll get into more detail on that this week. Because the p-value is very low, or because it's low or less than our alpha, I reject the null. So that means our p-value is very small and I'm surprised, so therefore there's strong evidence that the alternative hypothesis is true. And of course, this is going to be in context. So I'm never going to say the alternative hypothesis is true. I'm going to say there's evidence that shows that, and then write what that alternative was in context. Same thing for if it's larger than alpha. So if I have a high alpha, I'm not surprised because we're saying it happens all the time just due to random variability, just due to that random sampling. So I'm going to fail to reject. There isn't evidence to suggest that the alternative is true. Notice I'm never saying that the null is true. I'm just rejecting or failing to reject. So we looked at this example already, and we found our confidence interval for this. And now I want to use the same example and do a hypothesis test. So I'm going to use the same information that I did previously. So I put all of those values in. First, I found my normal probability plot. That helps me to check these conditions. Notice these conditions are the same conditions I checked for the confidence interval, so I'm not going to spend a lot of time on that. But here I'm saying I'm going to use a one sample t-test. For the hypotheses, I'm assuming that it says, does this data show a significant difference compared to the 55-point average that the high school teams have scored in the past 5 seasons? So 55 is sort of what I'm expecting to happen. I'm going to assume that these 10 scores are not going to be any different than that 55 mean that I've had over the past 5 seasons. So that means my null hypothesis is that it will in fact be 55. The mean number of points a high school team scores is equal to 55. Now, what I'm testing for is it says, does this data show a significant difference? Well, difference means that it's not equal to. Notice it doesn't say, are these teams scoring more than 55 or are these teams scoring less than 55? So that's my alternative, and of course then I just write it in words that it's different than 55. Again, just like last time, I used my calculator to find my 1-var stats for me. So if you're doing this, say, in a case study, I don't need to see all of this. I'm going to assume that you're using technology to find the mean and to find the standard deviation. Notice I'm going to find t for a specific number of degrees of freedom. So I'm going to take y bar, which is of course my observed value, which is that 57.8, minus whatever I'm hypothesizing. So remember, my hypothesis was 55. So that's going to go here. The standard deviation that I found divided by the square root of n. So notice here I'm doing t sub 9, and this just tells me, hey, I've got 9 degrees of freedom. So 57.8, which is my observed, minus 55 of my expected, and then I'm just calculating my t. This is my test statistic of 1.472, and just like always, that tells me how many standard deviations away from the mean is my value. Now this, as we know, because it's not equal to, is two-tailed. Because it's two-tailed, that means when I take this value and I essentially find the area to the right of that, that's the same. So whatever P I get here, that's the same as the value here. And so what I'm going to do, instead of finding this and then finding the area to the left, I'm just going to take whatever I get here and multiply it by 2. So notice I'm finding the probability that y is not equal to 55, meaning it could be, significantly greater than or significantly less than 55. So I'm going to take 2 times the probability that t is greater than 1.472. That was my test statistic. So I'm just going to find the one-tailed probability and then multiply it by 2. This one I'm showing you using your calculator, second and vars, and then you're finding the t-CDF. And then of course when I'm done, this is the lower, upper degrees of freedom. When I'm done, I take that value times 2. So that's what I get when I multiply it by 2. Now notice this is 17.51% of the time. So 17.5% of the time, I would expect to have this average if the 55 were true. And because this is a very high value, I'm saying I'm not surprised by that, which means I'm not surprised. There's not enough evidence to say that this sample that I found means that the mean high school scores are different than 55 points. Now, just like we did when we were dealing with confidence intervals, if you want to use StatCrunch rather than your TI 83 or 84, this is how you would check that normal probability plot, and this is how you would find those averages. So here's a question for you to try on your own, and I know that I haven't shown you yet how to do the t-CDF part in your StatCrunch program. I will on this example, but before I show you, I would like for you to do your best to go ahead and test this hypothesis on your own and then press play to check your work. So this should look familiar to you if you watched the video on confidence intervals. We already developed a confidence interval, which means we've already checked our conditions, so I'm not going to waste your time or mine by checking them again. For the hypotheses, remember that I'm looking for, does this exceed the 30-minute goal? So my null hypothesis should be that it's still, 300-minute goal. My null hypothesis should be that it is exactly 300, and my alternative is that it's going to be greater than that because that's what we're testing. So remember, null is always equal to, and it's always whatever it previously has been, that nothing has changed. Now for my calculations, again, I'm going to show you in StatCrunch, the actual test statistic I'm going to find by hand. So I'm using either my calculator or StatCrunch to find the mean of 306.25, to find the standard deviation of 29.31, and then I'm just finding my t score. And of course that is my test statistic of 0.7387. Now previously I showed you how to find this in your calculator using t-CDF. Now I'm going to show you in StatCrunch. So I'm going to go to calculators and then to t. And the only two things I need to enter are my degrees of freedom, which in this case would be 11 because I had 12 battery lifespans, and 12 minus 1 equals 11, and that's my degrees of freedom. So enter my 11 and my test statistic, which is the 0.7387. Notice I put 11 here and 0.7387 here, and this is a greater than, so notice that's the direction that I chose, and then this is my actual p-value. So that's what I get for my p-value. Again, remember when we did our interval, 300 was in our interval, and so we said, based on that we shouldn't be rejecting the null. This backs it up because this is a high p-value, so we're going to fail to reject the null. There's not strong evidence that the mean lifespan exceeds 300 minutes. And then notice I just stuck that same conclusion that I came up with previously back in here as well, which you might want to use when you're doing a case study. And the reason that it supports it, of course, is because 300 falls in our interval.